Hi, this video is a solved problem involving linear momentum. This is actually problem P3.55 from the problem sets, but it's a fairly complex problem, so I thought I'd do a video to explain the details. What this problem considers is a fluid here coming out of a nozzle. The nozzle's fixed, and so we have a fluid at some density, velocity, and cross-sectional area impinging upon a vane here. Now, we've done this problem before, and it's quite a simple problem, but the difference this time is that the vane is attached to a cart that's moving at some fixed velocity vc. So let's look at the problem statement here. So it says up here, it says, in figure P355, the jet strikes a vane that moves to the right at constant velocity vc on a frictionless cart. Compute A, the force Fx required to restrain the cart. And by this, by the way, they're not meaning holding the cart still, they're meaning keeping the cart from accelerating. So it's the force to restrain the cart so it has a constant velocity. B, the power delivered to the cart, and also find the cart velocity for which C, the force Fx, is a maximum, and the cart velocity for which the power is a maximum. What we're talking about here is the power imparted by the jet to the cart. So this problem involves the principles of conservation of linear momentum, and I want to emphasize that the jet here, the nozzle, is fixed. So it's not moving, it's the cart that's moving to the right at velocity vc. And so what we're going to do is we're going to consider a control volume that moves with the cart. So the difference in this problem compared to the other problems that I've solved in the videos is we have a moving control volume at constant velocity. So it's not accelerating, so we still have a non-inertial reference frame, so we can use our previous analysis. This problem is going to be done in a general way. So to obtain a general solution, I'm going to do the problem in symbolic form. So based on the previous video, recall that for steady one-dimensional flows in non-accelerating reference frames, we have the equation that I've shown here, that the sum of the forces on the control volume equals this term here is the rate of momentum flow out of the control volume summed over all the outlets minus the rate of momentum flow coming into the control volume summed over all the inlets. And we want to emphasize here that V is a vector quantity. In a two-dimensional flow, it would be two equations and two unknowns. And similarly, the sum of the forces is the vector sum of all the forces acting on the control volume. Now in this problem, we only have one inlet and one outlet, as you'll see when we solve the problem. And also, it's a little simpler. In this problem, we're only seeking the force in the x direction required to hold the cart at constant velocity. So we're only going to be considering the change in momentum here in the x direction, the outlet minus the inlet. The difficulty here and the difference is that we have a moving control volume. And so the V in that previous equation is the relative velocity. So what we're going to do is we're going to replace the vector V with VR, because we have a moving control volume to the right. And so VR here is the velocity of the fluid relative to the control volume. So for one-dimensional flows with a moving control volume, we can just replace the V that we had here, that vector V, with this VR term. And I think it'll make a lot of sense when I do the problem in a few moments. And the m dot terms here are the mass flow rates across the control surface, outlet and inlet, accounting for those relative velocity effects. So given that little bit of a preamble, I think now I can go to the touchscreen computer and we can try and solve this problem.
Okay, here we are with the Surface Pro 3. Again, we're dealing with a fluid jet issuing from a stationary nozzle here, and we have a moving cart. So the equation that we start with is that the sum of the forces in a vector sense equals m dot out VR out minus m dot in VR in, where these are vectors. What we have is the sum of the forces on the control volume equals the rate of momentum out minus the rate of momentum in, and we calculate these momentum terms using relative velocities. So let me redraw the control volume down here in a sort of at least a crude way, so we can work with it. So here's the vane. Here's the fluid on top of the vane. And here's the control volume. And so what we have is fluid coming into the control volume, and it comes in at a relative velocity equal to V jet minus Vc. Now let's just think about this for a minute, this relative velocity. If we set, for example, when the cart velocity is equal to the jet velocity, so when the cart and the jet are moving at the same speed, we would expect no flow onto the vane, right? And indeed, that's what we get. V jet minus V cart gives it the relative velocity equal to 0. And similarly, if we set the cart velocity equal to 0, then we get that the relative velocity just equals the velocity of the jet. And what we're after here, of course, is the force Fx, and I'm going to put it in that direction because realistically we know that to keep the cart from accelerating to the right, we're going to need a force to the left. So the fluid enters this red control volume. This is the control surface of the control volume. It enters the red control volume at a velocity Vr equal to Vj minus Vc. Now, as we discussed in the previous example with the fixed vane, we're neglecting the viscous shear, the drag, if you like, of the vane on the fluid. So the fluid here actually leaves at the same magnitude of velocity. So V jet minus Vc. It's going to have, that vector is going to have the same velocity, and it's going to have an x component, and it can be resolved in an x component and the y component. And so the x component here, u, is going to be equal to v jet minus vc cos theta, where this angle in here is the angle theta, and then there'll be a y component, which we usually give a symbol little v, equal to v jet minus vc sine theta. So we're only looking for the x component of force here. So it's asking for the x component of force, and there's no motion in the y direction, so the y component of force, while it'll be there, there'll be a value of Fy. It doesn't contribute to the power, which is the other part of the question. So we apply our equation here, sum of the forces, and we do it just in the x direction. Let me change my pen color. So what we're going to have is minus Fx equals m dot out Vj minus Vc. So the force in the x is in the negative x direction, so I have minus Fx equals the mass flow rate out of the control volume, and it's leaving with the velocity in the x direction equal to Vj minus Vc cos theta, and then minus m dot in, and then it comes in with this velocity Vr, so V jet minus Vc. Now we have to deal with these m dot terms. Now, we talked about this, that we're neglecting the friction of the vane, so the mass flow rate remains constant throughout. So m dot in equals m dot out, which equals rho a jet times v times the relative velocity, which is v jet minus vc. So it comes in at v jet minus vc, and this area here is a jet, and it has some density rho. So what we're going to do then is substitute this m dot here in there and there. Let me open up another page and scroll so we can see the problem here. So now I'm going to make this substitution, and I'm just going to do a little bit of rearranging as well. So we get that fx equals rho a jet. So I've brought the force over to the other side of the equation to get rid of the negative sign. And what we're going to have is we're going to get v jet minus v cart squared, right? So f is going to become positive, and that's going to come over to this side, minus rho a jet v jet minus v cart squared cos theta. And so now we can collect terms, and we get fx, the force required to hold the cart. It says stationary, or I forgot what it says in the problem here. If we go up, it says to restrain the cart. What it means is to prevent the cart from accelerating. So fx is the force required to keep the cart from accelerating. And we can collect terms here. We're going to get rho a jet v jet minus v cart squared 1 minus cos theta. And I believe that's the answer. Let me check. Yeah, that's the answer to part A. That's the force in the to the left required to keep the cart from accelerating. Now part B deals with the power. Let me scroll a little bit here again. What we're talking about, I'm going to use the symbol P for power. It's the power delivered to the cart by the fluid jet. So let me write that down. Power. So remember that work is, so W is the force, we're going to do it, force in the x direction times the displacement in the x direction, so force times distance. So then power, P, is the rate of work, is the time rate of work. So if we take the derivative of this expression here, fx times dx dt. Now dx dt is just the velocity of the cart. So it's fx, the force in the x direction, times the velocity of the cart. And so what we're going to do now is, let me do a different color here. We're going to take fx, and we're going to substitute it in here to get the expression for the power. Go back to purple here. So power then equals fx times vc, which equals, what we're going to have is rho a jet v jet minus v cart squared times the cart velocity, 1 minus cos theta. And that's the expression for the power that the fluid jet imparts to the cart. And I believe that's the answer to part B. Okay, part C. So what is part C? Part C is to find VC, the cart velocity that corresponds to the maximum force Fx. So find VC for Fx max, I'll call it. Again, I need a little more space, so I'm going to scroll. We have Fx up here, so it's too bad I got to Let me see if I can write it down before I scroll. We'll lose with that off the page. So that's our expression. And we want to find what VC gives you the maximum, what cart velocity gives you the maximum Fx. So what I'm going to do is I'm going to do this again later. I'm going to just set the density of the problem as a constant. Wow, or we can imagine it. If we're only considering what fluid velocity or what cart velocity gives the maximum force, rho a jet and 1 minus cos theta don't really come into the problem. We can set it equal to a constant. And so Fx then, some constant times v jet minus vc squared. And so I would say by observation now, and you could probably have done this earlier, but I just want to make it completely clear. By observation, any positive value of Vc is going to lower the force, right? You're going to subtract. So by observation, you can see that Vc equals 0 gives Fx max, right? So that corresponds to the maximum. So therefore, Fx max is just setting this equal to 0. So we're going to get, and I'll make the substitution back in for the constant. So we're going to get rho aj 1 minus cos theta, that's our constant, and then we're just going to get v jet squared. And that's the maximum force. Of course, when the cart's stopped, it's going to be, when it's not moving at all, you're going to get the maximum force between the jet and the cart. So that's the answer to part C. Now the answer to part D is a little more complicated. What we're looking for now for part D is the maximum power. So we want to find the cart velocity, Vc, that corresponds to P max. Now let me scroll and I'll just write down the power expression again. Now we had that power is equal to rho times the area of the jet, v jet minus v minus the v of the cart squared times the v of the cart, and then that times 1 minus cos theta. Now we want to find out what Vc maximizes this expression. So this is a classic first year calculus problem, right? We want to take dp dvc and set it equal to 0, and that'll find either the min or the max. But it'll be quite clear which is the min and which is the max. To make this a little less writing, I'm just going to do the same thing. I'm going to let c equal to rho aj 1 minus cos theta. That makes our life a little simpler. And so we have power equal to constant Vj minus Vc squared times Vc. And I'm going to expand this out. Take the derivative of that. It's easier if I expand it out. So that's going to be constant. And then we're going to end up with Vc cubed minus 2Vj Vc squared. I'm expanding this and then multiplying it by Vc, and that's going to become Vj squared, so plus Vj squared times Vc. Now we're going to take dp by dvc, and we're going to set it equal to 0. So this is going to become constant. 3Vc, right? 3Vc squared. And then this is going to become minus 4VJVC. And then this is just going to become plus, take the derivative of this term, V jet squared, and set that equal to 0. Let me scroll again. So we have the problem of 3VC squared minus 4V jet Vc plus V jet squared equal to 0, because we can get rid of the constant. And that's a standard quadratic equation. And just to remind you, this is like high school math. This is A, this is B, and this is C. And using those definitions, remember that VC equals minus B plus or minus, this must bring back some high school mathematics, plus or minus B squared minus 4AC all over 2A, right? And so what we have is minus B, so that's going to become 4VJ plus or minus the square root of, okay, B squared is at 16VJ squared minus 4AC. So 4 times 3 is 12, so that's going to become 12VJ squared all over 2A. Well, A is 3, so that's 2 times 3. And that gives VC, the cart velocity that either minimizes or maximizes the power, equal to 4VJ minus, plus or minus. So that's going to be 16 minus 12 is 4, so 4VJ squared. So this is going to be 2VJ over 6. And so when we do the plus, we get 6VJ over 6, so that's VJ. And when we do the minus, we get 2VJ over 6, which is VJ over 3. Now let's just look at these two answers and see which one is the maximum. If we put the cart velocity back up here, we have the expression for power, right? If you put the cart velocity here equal to VJ, what you get, you can see you get 0. So this corresponds to the power equal to 0. So this is obviously not a maximum. So the maximum power, corresponds to the cart velocity equal to the jet velocity divided by 3. Okay, let me scroll a little bit. Let me describe the behavior here. So what happens is interesting. If you look at the power imparted by the jet as a function of the cart velocity. Of course, we already talked about the case where the cart doesn't move, so the cart's equal to 0. You've got the highest force to restrain the cart, but the cart's not moving, so force times velocity equal to 0, so you have no power. Similarly, out here, where you have the cart equal to jet velocity, you have no fluid crossing the control volume because the cart's moving away from the jet at the same velocity, and so you have no transfer of momentum. And if you plot this curve, it looks like this. It comes down to 0 slope there. And the maximum here, the maximum power, so P max, occurs for the cart velocity equal to the jet velocity by 3. And if you plot the power function out, you'll see that that's true. And so that's the answer, that maximum power corresponds to when the cart moves at 1/3 the jet velocity. And that's the answer to, I think, the last part, which is part D. And that completes this problem.